Good afternoon. This is Professor Victor Ponce, and this is CIVE 638, Sedimentation Engineering. Today is Thursday, August 25th, and this is our second lecture, which I number 012. Our first lecture was 011. That was this Tuesday. Today is Thursday. The subject today is a continuation of what we were covering. Introductory material. Today I'm going to show 3 videos. I originally was going to show 2, but I do believe all 3 videos are very relevant to what we're going to say and what we are going to be discussing in this class. Okay, so now we're going to go on videos in here. And the first video I'm going to show is this one, Poechos Dam and Reservoir. I'm going to show you studies that were done in Peru maybe 3 or 4 years ago, which show the extent to which this reservoir has filled up with sediment so far. The reservoir has been operating since about 1975. So 75 says 25 plus 20. That's about 47 years of operation. So let's take a look at what this has produced in terms of reservoir sedimentation. And we are going to be looking at later on. Can everybody see that now, the video?
Yeah, we can.
By the way, I should tell you at this time, an interesting point of fact is that one of my first jobs as an engineer back in 1971 was on this site. The dam had not been built yet, so they sent a crew of engineers to figure out where was going to be, basically where was going to be the borrow sites for the material. And I was in charge, or I participated in that work back in the year 1971. So this dam here, it's a little bit in my heart because that's how I started as a civil engineer back in the early 70s. This, by the way, is the spillway, is the main spillway, one of 2 spillways actually. There's another bigger spillway. There's 2 spillways in this dam. It's a huge dam. And this spillway has a problem, erosion problem. If you can see in here, right in here, there's an erosion problem that they are been trying to solve for the last 5 years. There's the erosion problem. Can you see over here? There is recirculation in this filling basin, and that over the years, excuse me, maybe 10, 20 years, has been eroding the base of this spillway. So this, of course, has to be solved, and it is in the process of being solved. Can you see the erosion on the left side? And finally, we see in here the extent to which the reservoir has been filled with sediment. And this is in Spanish because the person that did this was local. He was a local engineer maybe 5 years ago. He was a good friend of mine, so he sent me this figure, so I posted it on the web, on the video. So this shows the accumulated sediment to this date. Actually, 2017, 55% of accumulation. By the way, this is a little bit unusual, but it's not uncommon, okay? Meaning it happens. This particular reservoir happens to be filled, I don't know, a little bit over half in 47 years, so that means it'll last maybe 30 more years. As a matter of fact, it has been known through studies that the El Niños, and there have been 2 or 3 El Niños in the last 50 years, are the events that are largely responsible for the bringing in a lot of sand into this reservoir. 1976, 2017. So that's the first video. The second video is one in Utah, which I did back in the year, I believe it was 2012 or 2013. This shows something I'm going to explain to you, something very fascinating. But let's just take a look at the video. December 23, 2012, I was there filming this video. Good afternoon. This is the Great Salt Lake of Utah, the largest saltwater lake in the Western Hemisphere. The lake is rather shallow. Its average depth is about 33 feet. Its salinity varies from 5% to 27%. By comparison, the salinity of the sea is 3.5%, and that of the Dead Sea in Jordan is 33.7%. The Great Salt Lake supports a population of brine shrimp, shorebirds, and waterfowl. Along with several other smaller lakes, the Great Salt Lake is a remnant of the ancient Lake Bonneville, which at one time... Look at the size of Lake Bonneville. That's the blue, the dark blue over here, and compare with the actual current size of the Great Salt Lake over here. Covered most of present-day western Utah. Bonneville Lake existed in the Pleistocene epoch, which ended 11,700 years ago. It covered about 19,700 square miles. That is, it was more than 10 times greater in size than the present Great Salt Lake. Lake Bonneville was a deep lake, about 1,000 feet deep, and its water was moderately saline, being able to support a population of fish. Its elevation was 5,102 feet, about 900 feet higher than the present level of the Great Salt Lake. I stress 900 feet higher than the present level of the Great Salt Lake. So it was a huge lake, and it was not as saline as the current Salt Lake. Lake Bonneville had a natural spillway at Red Rock Pass at its extreme north. Over here, it had a natural spillway. So eventually, when there was a big flood, it spilled over here into the Snake River in the state of Idaho. Bear River is the largest of 3 tributaries of the Great Salt Lake on its east side. About 15,000 years ago, the Bear River used to flow in a northwest direction into the Port Neuf River, a tributary of the Snake River in the Columbia River Basin. At about that time, lava flows dammed Bear River and closed its flow into the Snake River drainage, forcing it to turn south toward Lake Bonneville. The additional runoff brought by Bear River taxed the natural spillway at Red Rock Pass. Eventually, the high waters at Lake Bonneville produced a breach through the unconsolidated sediments at Red Rock Pass, causing a... Right in here was the breach. There used to be a natural dam in here, and it breached at about 15,000 years ago. Flood of catastrophic proportions. The flood that presumably originated due to the breach of that natural dam, has been estimated to be about the flow one to twice as much the flow of the Amazon River.
Prior to the breach, Red Rock Pass was at elevation 5,135 feet. Now it is at 4,789 feet. That is 346 feet lower. The drier climate which followed led to further shrinking of the lake to the present elevation of 4,202 feet and to its increase in salinity to a value from 2 to 7 times higher than that of the ocean. Salt Lake City and other local cities now sit on land formerly occupied by ancient Lake Bonneville, and Red Rock Pass now stands as a hydraulic relic of bygone wetter times.
Okay, the third video I'm going to show today is called the May 2011 flood in Cairo, Illinois. I did show you Tuesday a shot of the floodway, the Birds, what is it called? New Madrid, the Birds Point New Madrid spillway, or it's not a spillway, it's a floodway. So let's get into this right now. I got word right after May 3rd of the year 2011, I got word that the Army Corps had blown up a fuse, a levee fuse, over at Birds Point, and I decided to head out there. It took me a while to get out there, but I was there, I believe, as the video shows, on May 17th. So I was there roughly 2 weeks after the Army Corps blew the levee fuse. I'll explain later in more detail what a levee fuse is. By the way, this video is really fascinating. I was very lucky that I was able to do this. I learned a lot, and I'm sure you're going to learn a lot too. It goes on to prove that, as Machiavelli said, you can't win without losing. There's always a drawback to any project that we do, and we should examine very carefully what the drawback is and how to minimize its effects. And you'll see, if you really understand everything I'm going to say here today, you'll see what the drawback is and what could be and how it was fixed on site at that time.
Good morning. I'm standing here in one of the streets of Cairo, Illinois, and we are inspecting and visiting one of the sites of these sand boils that have popped up in the last couple of weeks as a result of the flood that is currently ongoing here in southern Illinois and northern Tennessee, in the location or in the confluence of the Mississippi and Ohio rivers. There is some reason to believe that this river, this underground stream, is going in this direction. As you can see, it has kind of loosened the soil in here. My name is Joe.
There's an underground stream in there, and you can only have a stream if there's a head. Without a head, you cannot have a stream. So where's the head? The hydraulic head. The hydraulic head is behind the levee that you will see right now, later.
George Pomeroy. I work for the U.S. Army Corps of Engineers, Memphis District.
In other words, We are here on the dry side of the levee, but we're going to get to see the wet side of the levee where the pressure originates that is going under these buildings and popping up at the street level.
We're on site here at a sand ball that is undermining the street, and it's pretty clear there that it's at various locations under here, under the towards the house, and just about everywhere out here in the middle of the street there's a possibility of sand balls.
To control the sand boil, the most effective method is to create a body of water above the sand boil to reduce the hydraulic gradient. Usually, if you reduce the hydraulic gradient to about half, the sand boil would stop. There would not be enough pressure to move the sand particles out of place and thereby cease to operate the sand boil, or the sand boil would cease.
How many of these sand boils have you had in the last couple of weeks here in Cairo?
Oh, somewhere in the neighborhood, maybe 25, somewhere close to it. Smaller balls, a lot smaller than this. We don't even ring them, but we monitor them, we watch them. If they get larger, then we put sandbags around them.
How do you intend to fix these boils after the flood is over?
Oh, this will all be dug out, and they'll come in here and they may put in riprap to try to stabilize the bottom. It's hard to say what we may encounter. We don't know yet until we get all this.
How does it all happen? It was during the flood. It was the flood of 2011. Now, the Mississippi River has a way of going to flood stage about every 20 years. So we had the flood of 73, which was very big, the 93, 20 years later, and the 211. I have not seen anything as high as 211 since. Right now it's 222, so in the next few years we're going to have a big flood too. It's every more or less 20 years. So interestingly, that this is the flood of 211, and all these sand boils, 23 of them, as the gentleman says, happened at that time. I don't have information as to whether these sand boils happened in 1993 or not. I don't know, and I don't think so, because the floods have a way of being different. So one flood may cause the sand boils, others, due to a duration and so forth, or stage, may not. But I don't have information on the 1993 flood, or for that matter, the 1973 flood. Those floods caused damage somewhere else in the lower Mississippi, not in the upper Mississippi. This is the upper Mississippi. Well, kind of middle to upper Mississippi.
Excavated out, and it'll be all the way curb to curb, probably back up in this lot behind you. And they have put down sheet piling in places to help try to stabilize the banks.
That's the flood wall on the side of the Ohio River. This, of course, was in May 17th, but on May 3rd was the peak of the flood, and we'll show you where it was, or what level did it reach.
We're standing here at the old flood wall, which is right to our immediate north here. And this is the new section here that was put in back in the 60s. I'd say somewhere around 63, possibly 64. I wasn't here at that particular time. And the new record now would be up in this area here, 61.7 feet, thereabouts. That was in sometime in May, possibly the 5th of May, maybe a little bit later. I'm not real sure the exact date.
How wide is the Ohio here?
Well, right now it's probably around 3,500 to 4,000 feet. That's from the wall there back over to the embankment back in the trees over there. Lewis and Clark started their expedition at this point right here. This is where their campsite was at back in 1803, before their journey up to Mississippi. So this is where it all began, right here. This is the area right here where the confluence of the Ohio and Mississippi rivers were back in the 1860s, and possibly even during Lewis and Clark's time. And back during during the Civil War in the 1860s, Grant came in here and captured Cairo for the Union, and there was no battle fought here. But they built a fort right behind us, which is over here where the sewage treatment plant's located at. They found a...
So now this gentleman is saying that a sewage treatment plant has been built on top of the fort that was built by Grant back in the time of the Civil War, 1860 and so forth, 65 or earlier.
Yeah, breastworks there when they dug out the foundations for the buildings over here, and they had found cannonballs still stacked. They found some rifle parts.
Listen to what he said. When they dug out the foundations for the sewage treatment plant, they found all those cannonballs. Cannonballs buried in the Mississippi River. What did that tell us? It tells us that it took 100 and how many years? 130 years to raise the level of the general terrain, perhaps 3 or 4 feet, so that the cannonballs will be buried. Is that true? Can this happen? Yes, it is. It happens that way.
Swords and other material that they had during the Civil War times. Fort Defiance is located right here where the sewage treatment facility is located at. That's the buildings over on the inside. And here we have the earth levees, which go all...
Note the flood wall. This flood wall is not going anywhere. I am not sure whether it is reinforced concrete, but I am telling you it's not going anywhere because it's extremely heavy. But that's not the only way we build. We have built levees in the United States, as this video will show.
All the way up the Mississippi River on the Illinois side here, and connect with other levees coming down.
Right there is the connection between the concrete flood wall and the earthen levee on the left. The entire city of Cairo is since it sits on the confluence of the Mississippi and the Ohio, it has been levied through the years. And I believe it is the largest or perhaps the only town in the U.S. or city in the U.S. that it is completely surrounded by a levee. I'll talk about more about this later on.
And this is for the new wall here that they incorporated the old wall inside in this particular location. Down there in that group of trees straight down below us down here, and this backwater here, this is all from the Mississippi River. Down there in those trees down there is the confluence of the Ohio and the Mississippi.
Okay, there's the Mississippi River here on the left and the Ohio on the right. Mississippi is coming out a lot more sediment, as you can see, because the Mississippi is coming, the Missouri is coming from dry areas on the west side to the west. The Ohio is coming from wetter areas to the east, from Virginia, West Virginia, and so forth. So it has less sediment, as you can see. This is the city of Cairo, Illinois, in southern Illinois. And as you can see, it is surrounded by a levee right here. That's the levee, right here. Completely surrounded by a levee.
It's not available at this present time. There's no way to get to it. but that's where the two rivers come together. The Ohio ends there, and the Mississippi continues on south to New Orleans. Over here on the left-hand side here, we're standing on an earthen levee. This helped protect Cairo there during this previous flood and in the past floods. And over here on the left.
What do you guys think would happen if the Mississippi would come in very high and overflow the levees? That would be the end of Cairo. Because, well, it depends on how much it flows and how much it breaches and so forth. Of course, it's the job of the Army Corps of Engineers not to let that happen. That's where they're there.
Left is the Mississippi River. Back over here on the other side, these trees, small trees, and that is the community of Cairo. And
the purpose of the Birds Point, New Madrid floodway was precisely that, to control the flow of the Mississippi so it wouldn't overflow the levee.
it got within 3.3 feet of overtopping the levee.
Tom Morgan.
This gentleman over here is the civil engineer in charge of the flood fight. And I believe he had been there for 2 or 3 weeks and he was getting ready to leave because his job was almost done. Tom Morgan, he is with the Army Corps of Engineers in Memphis. He happens to be a geotech. That's fascinating, interesting. Why a geotech? Why not a hydraulic engineer or a sedimentation engineer? And the answer is that the situation in there is the situation that needs to be fixed in there is half geotech and half hydraulics. So at that point, what do you choose? Obviously, the geotech went in. The geotechs went in.
I'm with the U.S. Army Corps of Engineers. We're out of Memphis. I'm the area commander for the Cairo area during the flood fight. Basically, what we got here is a sand bowl that's underneath the street. You can see it all along the joints in the street. You can see it kind of bubbling up, and you can see some movement of material from underneath the road bed here. This whole section was bubbling up at one time at its peak, and it's starting to settle down now. But eventually, enough material will come out from underneath the street that will have to be repaired. You can see it already sinking down, bubbling over there. We tried to sandbag this area to some degree to try to get water, and it was successful to get water over the boils at the time, and it did subside, but it seemed to push the pressure out away from the initial points up there.
This is the largest sand boil ever recorded, ever constructed by the Army Corps, 30 feet by 40 feet, Cairo, Illinois, May 18, 2011. I was very lucky to be there and be able to record this event for posterity.
This is a very large sand bowl that we're looking at right here. We estimate it to be could be up to 24 inches in diameter.
The pipe, the hole is estimated by Morgan to be 24 inches in diameter. That is really amazing. How is that being caused, by the way? What is causing it? The pressure on the other side of the concrete wall over a couple of weeks.
Road, and it developed when the river stage was about 59 feet on the Cairo gauge.
The 59 feet on the Cairo gauge started developing this sand boil.
We figured at that time there was about a 20-foot head, at least a 20-foot head over this.
20-foot head over this place. 20-foot head of water.
Area. What we've done is try to ring the boil, and we put approximately 10 to 12 feet of water over the top of this sand bowl so that we minimize or that we reduce the head over the sand bowl. Therefore, what we're looking to do is stop the flow of material, the piping of material from under there. from the sand boil. We're still letting the water flow, let it flow clear. It reduces some of the pressure, but we're trying to minimize how much material that is piping from under the ground. We think we have it under control now. It's dropped about 2.
It is obvious that if you had a whole lot of material being piped under the ground, that would endanger the stability of the concrete wall. Dig a hole under it, which didn't happen, by the way, because these guys were there early and assumed control of the situation to try to control it, and they actually effectively controlled it.
Feet.
Until the next flood, which will be in 20 years.
We continue to lower our sandbags here so that we continue to get flow, so that we don't risk this from popping up somewhere else.
This is on the other side, on eastern Missouri, on the border. We're here on the border between Missouri and Illinois. So I went over there to check out the levee fuse. I wanted to see with my own eyes how the local situation, and perhaps even video the site where the Army Corps had 2 weeks earlier blown the fuse in order to let the water go into the floodway.
This is Bird's Point, the Madrid floodway. The breach area is back over near the right of the smokestack that you see over Kentucky. The trees are at, that's where they put the levee.
There's the breach area. Can you see it? Right there. They blew the fuse, I believe it was on May 3rd. That was exactly 2 weeks, or roughly 2 weeks, before I was there.
The Levee Breach is at a place that they call Bird's Point. Over there, about a couple miles from here, and you can almost see the breach over there to the left of the trees in the middle of the floodplain. This is the Bird's Point floodway here in Missouri. This breach was operated for...
You can see over here, this is where we are right now. And this is Bird's Point, New Madrid. And this is supposed to hold the water, the flood waters, to reduce the pressure on the entire system and also reduce flooding downstream.
Put into action to relieve floodwaters from the Mississippi on or around May 5th. Today is Wednesday, May 18th, 2011.
Interesting to note that the floodway had been operated in the year 2011 only for the second time. So 1937 to 2011 is about in 80 years. In 80 years it had not been operated because it is a safety measure. And prior to that, they didn't feel it was necessary to operate the relief. Okay, so these 3 videos show extensively what are we doing here? We're sitting here trying to learn sediment, but it's sediment moved by water. So it's really hydraulics and it is geotech in some sense. You can call it both if you wanted to. You can see Mr. Morgan was a geotech engineer and not a hydraulic engineer. And he was in charge because this particular problem of the sand boil happens to be more a geotech problem than a hydraulic problem, even though it does have water in there too. But it doesn't matter whether it is geotech or hydraulic, it is a problem that we all civil engineers have to face with. So right now I'm going back to reality here. So I'm going back to the syllabus, and I'm going to be going into still on sediment properties. We haven't finished this. Let me increase the size a little bit. And we had talked about particle characteristics, the shape, the specific gravity, the fall velocity. I believe we covered that ground already. And I urge you to examine the examples. I'm going to talk briefly about, I believe, repeat what I had just said on the example 13.2. The example 13.1 is a direct application of equation 13.2 to calculate the fall velocity. This is the excuse me, the fall velocity given C sub D, which is the drag coefficient, and D sub S, which is the size of the sediment, we can calculate directly the fall velocity. But the drag coefficient is something that is not readily known. So the only other way to solve this problem would be to do an iteration. And that's what I intend to show you here right now. The drag coefficient is not known a priori. In this case, an iterative solution is warranted. And again, the solution can be done by hand. Nobody does things by hand anymore. Or you can use an Excel sheet, or you can use one of our calculators. A particle Reynolds number is assumed, and the drag coefficient is obtained from figure 13.1. So from here, assuming a particle Reynolds number, we find the drag coefficient from the solid line. Remember, over here is laminar, leading to Stokes' law, and over here is turbulent, and turbulent it's because it's not a specific function. It has to be done by iteration, by trial and error. So we assume a particle Reynolds number. Fall velocity calculated with equation 13.2, and then a Reynolds number with equation 13.3, and once we do that, the iteration is continued until there's sufficient agreement between assumed and calculated Reynolds number. Procedure is illustrated by an example. So we're given in here the diameter, which is readily determined by grain size analysis or whatever, and the water temperature, because we need the water temperature in order to figure out what the kinematic viscosity should be. So we set up an iterative procedure, and we've done this in the calculator online fall velocity. Assume a Reynolds number, Reynolds old, calculate the drag coefficient from that figure, and you got to go in there, since it's not analytic, you got to go in there by a procedure which I have already referred before. It's called piecewise linear approximation or interpolation. Calculate the fall velocity, calculate the new Reynolds number, and calculate the difference between the new and the old Reynolds number. If it's the same, then you're done. If it's not the same, then you use the new Reynolds number as the old Reynolds number and proceed. So now in here, we're going to try to do this. I'll show you how it works. This is a sample test. I'm sorry. Test, okay. The units, I believe the units we were talking about here is 0.1 millimeters, right? 0.1 millimeters, and water temperature 20. See if we're okay here. See if we're, yeah, that is correct. That is correct. So we did an iteration on this formula based on the procedure that I've already established and told you about. So we have metric units, or US, this is metric units. This program iterated 12 times among these procedures, these equations. 3 or 4 steps, 12 times. There's 36 steps. Why did it so fast? Because the servers that we use nowadays, the computers that we're using are extremely fast. It was blink of an eye, right? It was not even a second. Number of iterations, we figured out what the drag coefficient was, the final drag coefficient after the iterations, the particle Reynolds number, and the fall velocity is 7 millimeters per second. 7 millimeters per second. Okay. The size distribution of sediment deposits. Why do we do this? Because oftentimes we have to deal with sediment deposits. in the reservoir, particularly in the reservoir, as I already shown you in the video that we've seen today. You need to figure out the weight. If you have the weight, you can figure out the volume or vice versa. So important property is the size distribution. No, not the, well, the size distribution of the individual particles. So how is the size distribution determined? By sieving, if it's sand, or by some other method, which I'm going to talk about right now. Typically what happens is that the sieving of sand particles is a geotech solution. But in hydraulics, we don't use that because we don't need a whole lot of accuracy in the particle distribution. So a methodology which is called the visual accumulation tube has been developed and is used for this purpose. And I'm going to show you an example of that right now. As it says in here, the size distribution can be measured in many ways. The coarses fraction can be separated by direct measurement for boulders and cobbles. In the sand size, what is used in hydraulic engineering and sedimentation engineering is the visual accumulation tube, which is a fast, economical, and accurate method of determining the size distribution. In the VA tube, the particles start falling from a common source and become stratified according to their relative settling velocities. At a given instant, the particles coming to rest at the bottom of the tube are of a certain sedimentation size, finer than particles that have already settled and coarser than those still remaining in suspension. Okay, so I'm going to give you now, I'm going to show you a, let me see if I can do that. Yeah, right. Visual accumulation. This is the original paper. I pulled it out of the web, hopefully. We're lucky here. It's taking a while to load this. I hope it does. But at any rate, this is a report that was put together back in the year 1955. It's not doing it. You know, PDF sometimes plays dirty tricks on us. Well, okay, there it is. I'm sorry. I'm sorry I said that. Visual Accumulation 2 for Side Analysis of Sands by Colby and Christensen. Mr. Colby is famous because he is the one behind the modified Einstein method. And how he developed the Colby method by using the modified Einstein method. And we will examine in detail the Colby method later on as we get to the calculation of sediment transport in the second part of this course. Colby and Christensen wrote this paper in 1956, and they were working as part of the Federal Interagency Sedimentation Project, which, by the way, is still active. It's really surprising that after so many years, the Federal Interagency Sedimentation Project is still active. They are the ones that developed the equipment for the Army, for use of the Army Corps of Engineers and anybody else that wants to use sedimentation equipment. So these people are with the Waterways Experiment Station in Mississippi, Vicksburg, Mississippi. So this report, this is an ASE report, by the way. It's an old report because they don't use this format anymore. But it is an ASE report. It's still good. Has not been, this work has not been redone or improved. It's still there. And the equipment is this equipment. So the way this thing operates is that the sample is dropped over here, and by the time it gets down here, it is stratified. It has stratified into various sizes. And from here, there's a recorder, and you can plot the stratification and therefore develop the size analysis. So that's basically it as far as the visual accumulation. You may be curious, or we all may be curious as to find out how much would it take, how many dollars would it take for us to get ourselves a piece of equipment like this? And I've done that in the past. I haven't done it yet, but I've done the querying, or the asking about how much would it cost. There's a company actually that sells these types of equipment, and I do believe that the VA tube prior to the pandemic, I don't know, after the pandemic things got messed up, right? But prior to the pandemic, it was about $6,000 that will get anybody this piece of equipment to put it up in the lab or to use it for analysis. Okay, so that's the report of visual accumulation 2. And then we have in here, let me see what we are in here. We go back in here, I think. Yep. Yeah, we already covered that ground. So we're back in here now. Okay, the specific weight. The specific weight is the dry weight per unit volume of sedimentary or sediment deposits. And we need to have a formula to calculate that. We can actually go out there and measure it. The problem is that when you do a measurement is always good, but it's only a measurement at a point, right? There are formulas to calculate specific weight and also to calculate the variation of specific weight with time, which happens in clays and silts, particularly clays. They have a way of settling slowly depending on the type of operation of the reservoir, and therefore there's some variability in the specific weight. And the specific weight is a piece of information that is required when sedimentation of lakes and reservoir is carried out. Okay, so we have in here a methodology which was developed by Lane and Kelsey. And by the way, these two people, these two gentlemen, used to teach at Colorado State. Lane was actually a professor at Colorado State. He was a professor of my professor. So basically, he becomes your, I guess you could say, your academic grandfather, because he used to be the professor of Daryl Simons, who was in turn my professor. Kelsey, I didn't get to meet Lane because I believe he was already gone by the time I got there. But I did meet Kelsey, who was obviously younger than Lane and was there at the time I was there back in the middle 70s, Professor Kelsey. So he was responsible for developing this methodology with Lane. And I believe, when did they do this? This is interesting. When they do this? Okay, let's take a look. Lane and Kelsey, 1953. Let me see if I can go back to where I was now here. In 1953. So these are very old. Okay, here we are now. We're back where we are. So this formula 13.5, which says that the specific weight of a sediment deposit is equal to an initial specific weight measured after 1 year of consolidation, plus an increase with time. And the increase is given by this formula, which is a kind of a logarithmic variation developed by Lane and Kelsey in 1953. And so the properties are in here. This kind of shows that in time, the specific weight of sand is not going to vary because the B, the coefficient of the time, is 0. But the silt would vary and the clay would vary a little more, depending, of course, on the way of operation, the mode of operating the reservoir, which varies between sediment always submerged or nearly submerged, or normally a moderate reservoir drawdown, normally considerable reservoir drawdown, and reservoir normally empty. So in this case, we use these numbers in order to generate the specific weight. And this is the range of specific weight in sediment deposits in pounds per cubic feet. Note intently that the specific weight of water is 62.4. So this has to be either a little less or a little more than 62.4. Why do I say a little less? Well, they are sediments. Sediments could be, their specific weight could be actually less than water, as this table shows. In case of clay, it's 40 to 60, so clay is always less. When it's aerated, then it becomes a little higher. It gets all the way to say 80, which is more than 62.4. And as you can see, you can analyze these numbers and realize what the variability in specific weight is between the type of sediment. And typically, the soil that we encounter in the field is kind of a combination of silty clay or sandy silty clay. In agricultural engineering, it's called a loam, L-O-A-M. A loam is a soil that is very good for agriculture. We in engineering, we don't typically use that word, but we recognize that the word is out there. We would like to talk about mixed soils like sand, silt, and clay. And typically the soils out there have a percentage of sand, percentage of silt, and percentage of clay. So in here you see sediment, clay, silt, clay silt mixture, sand silt mixture, sand silt clay mixture. This is the more common one, in my opinion. Although it does vary where you are. Sand and gravel. The existence of sand and silt depends a lot on the location, the geomorphology, the time, the weather, all kinds of other things. And we have an example here to calculate the Lane and Kelsey formula, which is extremely straightforward, and we have already done that. See, it says in here, calculate the specific weight of a sediment deposit in a reservoir after an elapsed time of 50 years, with the sediment always submerged or nearly submerged. So we're going to be taking these numbers in here. Always submerged or nearly submerged. We're going to take the B 5.7 and the B 16 for the clay portion, for the silt and clay portions. Okay, so we have sand 30, silt 45, and clay 25. So we can operate this thing in here. Elapsed time, was it metric in here? Let me see. No, it is U.S. customary. So it's U.S. customary. Elapsed time 50 years. What did I say? 30, 20, 30, 45, and 25. I believe I did say that. Let's check. 25. Yeah, it's correct. And sediment always submerged. So we do the calculation, and it comes out to be 75.8 pounds per cubic foot. Is that correct? Yes, it is correct. Okay. So we're back in here now. Any questions so far? Okay, initiation of motion. That's the next subject that we need to cover here. Initiation of motion. That is part of our sediment transport, which we'll get in there eventually. But I need to cover initiation of motion at the beginning. So this is where I'm going to go there. I'm going to go there where it says initiation of motion. But over here, right there, initiation of motion. But before we start the discussion, or rather the presentation of initiation of motion, I wish to call your attention to this color graph in there, which is an extremely important piece of information for all of us. Again, I was lucky when I wrote this book more than 30 years ago. This is part of my hydrology book, by the way. But I thought at the beginning, when I did the hydrology book, that I was teaching hydrology at the time, not hydraulics. So I figured, I said, well, when am I going to get to write a hydraulics book? And it was not in the horizon. So I said, I'm going to put sediment into the hydrology book, because sediment could be the hydrology or hydraulics. There's a lot of hydrologists out there that have dedicated their lives to studying sediment. One of them is Professor Nordine, who was over at Colorado State, and quite a few others that are sedimentologists or sedimentation engineers and consider themselves hydrologists and not hydraulics people. Suffice it to say that it really doesn't matter. You know sedimentation and that's it, right? Okay, so whether you call yourself this or that, it doesn't really matter. We're all civil engineers anyway. I should make an exception. Not everybody that studies sediment is a civil engineer. That is a fact. There are geologists out there, and even, and I say even with tongue-in-cheek, even geographers study sedimentology. Several months ago, maybe 5 months or 6 months, I had a discussion and experience with a couple of people from Holland. And they were professors out there. I believe one of them was Dutch, and the other one was either British or from Holland, working out of Britain, whatever it was. They were interested in the work that I had done on the Bedernikov number. And these people were sedimentologists, but they called upon me to explain to them some of the work that I had done. And they were very keen in finding me, and asking me all sorts of questions, by the way. They had a lot of questions on my work because they wanted to do a good job. They had been asked by the editor of a sedimentology journal. Look at this, sedimentology journal. And typically in a sedimentology journal, civil engineers don't write there. I should say that honestly. The Sedimentology Journal is for the sedimentologists originating as geologists, right? But they felt strongly enough to talk to me because they knew I knew the hydraulics because I had put it together. They really wanted to find out all about the Vedernikov number. And since I am the so-called expert on the Vedernikov number, they reached out to me and I spent a lot of time with them. 2 or 3 meetings, Zoom meetings, about an hour and a half, explaining to them for clarification what I had said in my papers on the Vedernikov number, because they felt, I believe quite correctly, that there's 2 numbers in hydraulics, the fruit number and the Vedernikov number. And the fruit number was known very much for many years, but not so much the Vedernikov number. The Vedernikov number is quite a discovery of the last 20 and 30 years, and that should be considered to be relatively new. So they engaged me and I helped them out, and hopefully they're going to go out there and improve their paper that they're writing for a sedimentology journal. So as you can see, there's a lot of interaction between the fields. There is nothing that belongs to any field whatsoever. Everybody can really kind of hit and miss and, do what they have to do, like these 2 gentlemen. Very nice gentlemen, by the way, that wanted to do a great job and wanted to find out all about the Vedernikov number. And I guess they talked to the right person. We have extensively written on the Vedernikov number, and which is a subject of hydraulics, by the way. And I'm not sure we'll have a chance to get there in this class, but we'll see. Okay, so having said that, I am going to talk about this graph extensively right now, because we need to understand this graph as we start our study of sediment. I ran into this graph in a paper. The reference is 11. Let me check it out. The reference 11 says Cooper and Peterson, 1970. And it was a discussion. I can't believe this. What luck. A discussion is not a paper. A discussion is a corollary on a paper. And these gentlemen put together this tremendous graph as part of a discussion. That's really amazing. But that is a fact, because this is a graph that explains just about everything that is to be explained. Without this graph, we would be buried in semantic confusion. We wouldn't know what we would be talking about. So the relationship between 2 classifications of sediment load. There's a classification based on predominant mode of transport and another classification based on whether particle sizes are represented in the channel bed. So as far as the predominant mode of transport, we have suspended load and bed load. And as far as whether the particles are represented in the channel bed, we have wash load and bed material load. And right there is the confusion. It's all sand, silt, and clay, right? Particles, different sizes, but particles nevertheless. And these particles are moved by the water. And the water has different ways of moving the particles. If the particles are heavy, like in the case of sand or even gravel, the weight will be of importance. But if they're not as heavy like sand and silt and clay, then the weight becomes of lesser importance. And perhaps in the case of clay, clays and colloid particles. It is the chemistry that interferes or interacts with physics. And we get to a point in here where we don't know if the problem is a physical problem or a chemical problem. And engineers, particularly civil engineers, are very aware of physics because we have been learning physics forever, but not so much chemistry. We need to learn a lot about chemistry. And in many instances, that is where we fail. Meaning the failures are because we fail to consider the chemical aspects of the sedimentation problem. But having said that, let me go back to the chart in here, or to the figure. So we call it suspended load, everything that is being suspended in the profile. And bed load, the stuff that is not suspended. It is still moving, but it is moving by sliding and jumping. Jumping and sliding, sitting on the bed, coming down to the bed and being moved downstream. As you can see, rolling and sliding on the bed. That's called the bed load. The suspended load is not bed load, okay? However, over here, we have a slightly different view of it. we have a situation where if the particle sizes in the profile are not represented in the channel bed, then that would be called wash load. Otherwise, it's bed material load. Now, if you haven't been thoroughly confused already by the semantics, so be it. When I studied this maybe 30 or 40 years ago, I was also confused. There's not much we could do about it. All we need to do is just learn the various divisions. And finally, the total sediment load. What is the total sediment load? It is composed of wash load, suspended bed material load, and bed load. Can you believe this? It's really amazing. But I want you to look into this very carefully and understand. So when I say suspended load, I mean this. When I say bed load, I mean this. And I'm talking about the predominant mode of transport. If I say wash load, I mean this, and I'm talking about whether the particle is represented or not in the channel bed. If it's not represented or not in the channel bed, the originators of these concepts maybe 40, 50, 70 years ago, they called it wash load. As a matter of fact, I believe it was Einstein, one of the first ones to call this particular concept wash load, as opposed to bed material load. How does this happen, or how does this originate? Well, typically, rivers out there that we care to study are sand bed rivers. There are some sill bed rivers, but they are, excuse me, let me get a little water here. There usually is some silt in the bed of the rivers, but this is in the estuaries, typically not in the mainstream or the valleys. You know, we have the mountains, the valleys, and the estuaries. And in the valleys is where most of the development is going on. So therefore, we kind of center, and by degree of economic importance, in the valley. So therefore, we end up looking at a whole lot of sand bed channels. That doesn't mean to say that all the sand channels are sand bed. It's just that 90% of it is sand bed, and that's why we become experts on sand bed channels. But there are gravel bed channels upstream, and there's silt bed channels downstream. As you can see, the difference does vary. And the issue of wash load is very important, or very distinctly important, because in a cobble bed, the sand is wash load. Right? You don't see the sand. And the sand is really not part of the bed. So therefore, the sand in a cobble bed would be wash load, would be considered to be wash load. But when it comes down into the valley, it turns into suspended load. So you see the dynamics of the situation. That's why it is so difficult. That's why Einstein, the elder Einstein, told his son, this is the difficult subject, so you're smart, get into it, right? So I'm saying the same thing. You guys are all smart. I'm assuming you're all smart. So you could get into this. It is a fascinating field, and it is also very important from the standpoint of society. And many of the blunders that are out there committed on a daily basis are committed by engineers that do not know or cannot call the expertise to solve a problem correctly.